First of all, I wanted to thank the Spanish Astronomical Society for inviting me to give this presentation on the next decade for solar and heliospheric physics. The last thing that I thought when I said yes is that I was going to give this talk in the middle of a pandemic. Here in Colorado, it's 3:30 for me. It's really early in the morning, but I thought it was a great opportunity to explain to the Spanish community what I think is going to happen over the next decade in solar physics. So I decided to wake up really early in the morning. I have coffee with me, but if I fell asleep, someone please wake me up. Okay, so I think there was already a talk this morning on gravitational waves. Gravitational waves is the main component of multi-messenger astronomy, and the combination of gravitational waves and telescope detections, the electromagnetic counterpart, is what we're calling multi-messenger astrophysics. So what I want to explain to all of you is that there is also something that is a multi-messenger era for solar and heliospheric physics coming over the next decade, thanks to a number of missions, space missions, and telescopes. And I will explain the context and the physics that we're trying to solve. In particular, for the physics, what we are really trying to understand is what I say here, which is how stars and planets are magnetically connected. This has implications in the case of the Earth, is about the space weather produced by the sun and everything that produces here on Earth for our technology. So these are a very practical component of this magnetic connectivity. But we now know that also for the habitability of planets that are orbiting M dwarfs, there are a number of exoplanets, including Proxima b, that are really close to the star, parent stars that are very active magnetically, much more active than the sun. And we now know that habitability conditions really depend also on whether they are being bombarded by these magnetic explosions that occur on the stars and also on the sun. The sun here is acting like a Rosetta Stone for this magnetic connectivity. That's what we're going to try to investigate over the next decade. And the reason why we're going to make progress in this area is mostly due to these missions that you see here and the ground-based telescope that the National Solar Observatory is building in Hawaii, the DKI Solar Telescope, DKIS. I'll explain the context of the missions, and then I'll go into some science use cases that explains this magnetic connectivity. In the case of the sun, we are calling this a multi-messenger era because we're measuring. We have different messengers as well as in the case of multi-messenger astrophysics. So what this is the Parker Solar Probe. This is a NASA mission launched in 2018. Parker Solar Probe has done already 5 encounters with the sun. This is Solar Orbiter launching this year, in February this year, that is also going to get closer to the sun. These 2 missions are encounter missions. They're approaching the sun, and they're measuring particles and fields locally where they're flying through. And what we want to know is these particles and fields, how they do originate on the sun, find the electromagnetic counterpart. And the way of doing that is by using telescopes that can be either in the mission Solar Orbiter. Solar Orbiter does have telescopes that observe the sun. Parker Solar Probe does not, or with a 4-meter telescope that we're building here on Earth in Hawaii, 4-meter class telescope. And this is the combination that is going to really enable this multi-messenger era for solar physics. Here, I want to again kind of put in context what we're trying to do. What you see in this circle here, that's what I want you to focus, is the heliosphere, the interplanetary medium. Here you have the sun. Let me find it. This is at the center, and this is the Earth. So this is one astronomical unit. And what you see is what we call the Parker's spiral. These are magnetic field lines that come out from the sun and that actually dominate the entire heliosphere and go and find the galactic magnetic field. These are the open magnetic field lines that form this Parker's spiral. The solar wind is streaming, flowing out past these spirals that you see in here. And from time to time, the sun is going to have an explosion that is going to perturb the spiral from the Parker's spiral. And this is what is happening in here. This is the Earth. So this is one astronomical unit. And if you go to here, this is stereo A. This is a NASA mission. This is in 2012. So Parker Solar Probe and Solar Orbiter were not flying yet. This is a space weather prediction from NOAA. So there are simulations here, and there are that are coming from data, that are coming from numerical models of what is going on in the interplanetary medium. And for stereo A, at that time, it was being impacted by 3 coronal mass ejections. One over here, and one here. So from one astronomical unit, these explosions span and they dominate the entire heliosphere. It's really hard to tell what a stereo A is measuring, whether it's coming from this CME, or from this other CME, because they're all combined, and a stereo A is measuring the result of all 3 of them. So what we want to do is getting closer. By getting closer to the sun, you are more able to say, okay, these particles that I measure, these electrons, these protons, these magnetic fields, are coming from that one explosion that occurred on the sun. And you are more able to isolate what is the specific process on the sun that did have an interplanetary consequence in terms of plasma waves, in terms of radiation. So that's why both ESA and NASA have decided to have Parka Solar Probe and Solarimeter. Both of them are getting closer. It's like getting higher spatial resolution. You are able to say these interplanetary consequences are happening for that physical process on the sun. And once you have identified the physical process on the sun, what you want to do is put the best telescope you have with the best resolution, with the best sensitivity to really understand the physics of what's going on and say, okay, all of these magnetic processes are what are leading to the particles that they measure in situ. And that's where DICIS comes into play. DICIS is a 4-meter telescope, and so will be the European Solar Telescope that the IC is leading for the Canary Islands. They are 4-meter telescopes, and I know that some of my nighttime colleagues have a hard time understanding why solar astronomers do need 4-meter telescope, and the answer is same as you, is for photons and resolution, same as in nighttime resolution, in nighttime astronomy. In solar physics, what we need to have is moving to this parameter space, a signal to noise ratio of 10 to the 4. We need to have a resolution of typically 0.1 arcseconds and a temporal resolution of 10 seconds. These 3 parameters, force the solar telescopes to be 4 meters. So you just put these numbers into here, into the equation that gives you the exposure time for a star at a given telescope. Here I'm solving for the diameter of the telescope. You just put these conditions here and you get 4 meters. That's why DICIS and why the ESTR of 4 meters. Solar physics is not here. We can achieve 10 seconds, we can achieve 0.1 arcseconds, but then we get only 10 to the 3 signal to noise. If we reach out to 10 to the 4 in signal to noise, then we'll have more several arcsecond resolution and minutes temporal resolution. So the energetic processes that happen on the sun require us to move in that direction. That's where we're building telescope of this size. We already got the first images with the Daniel K. Inouye Solar Telescope. And we were really delighted to see that the New York Times got our images and put it on the front page above the fold. That's what you get when you go to the kiosk and buy the newspaper. And we were absolutely delighted. I tweeted it, and Didi Claus, known to all of you, I'm sure, retweeted my tweet. So this is the most success, the highest success that I have had in social media. Was totally happy. We are now in the latest phases. This is a commissioning imaging. We are not done with the telescope. The telescope is now impacted by the COVID-19 situation, but we're hoping to finish the telescope sometime this year, really depending on how the pandemic evolves. One other important property of the Daniel K. Inouye Solar Telescope in Hawaii is that it is off-axis. So it has no central oscuration. It's 4 meters and it's off-axis. So here you see the diagram, and here you see the image of the telescope. You can compare with the person here, a couple of people of our technicians. So it's really large. It's really a huge facility. And the off-axis is really important because it allows the solar light to directly hit the primary mirror without any central oscuration. And we get the primary images in a way that has produced minimum stray light. We are trying to minimize the stray light, a central oscuration, a secondary that hits the light that is on its way to the primary mirror will produce always a stray light. And this will be a problem for our observations of the solar corona. By being off axis, DICIS will let us observe something that is very, very faint, like the solar corona. We also need an oscuration to block the direct light of the sun to see the solar corona. We have LIOT stoppers on the telescope. but thanks to the off-axis and the Lyot stopper, we're able to observe the solar corona. I'm emphasizing this because really the observations of the solar corona is what is gonna enable this multi-messenger era. Parker Solar Probe is a mission that is actually entering the solar corona. And here the definition of the solar corona is the subalvenic region, is the region where the solar wind is still being pushed by energetic processes that we don't understand on the sun. So the whole idea of Parker Solar Probe is to go inside the solar corona and actually measuring in situ properties like particles, solar wind particles, energetic particles, and fields, electric and magnetic fields. Being that close to the sun is really hard to put a telescope. Parker Solar Probe doesn't have a telescope that is directly observing the sun. So it's kind of blind, it's flying blindly, but it's telling us a lot about the physics, thanks to this in situ sensor that is flying through the solar corona. Hasn't reached out yet to the subalvenic region of the sun. It is still flying in the superalbenic region, but this is something that is going to happen over the next encounters, and soon will the Parker Solar Probe will fly through this inner corona, through the corona of the sun. But already in the superalbenic region, it has found really interesting results that I'll mention at the end of my talk. Solar Orbiter is not getting into the corona, but what it's doing is understanding the magnetic connectivity of the sun, and for doing that, it's going to use a number of telescopes observing the sun and a number of in situ instruments. I want to emphasize a couple of combinations that allow this magnetic connectivity. One of the telescopes is a SPICE. SPICE is an ultraviolet spectrograph that measures composition on the sun. And then the solar wind analyzer measures composition where the satellite is flying, where solar orbiter is flying. By measuring the composition on the sun and locally, and if it is the same composition, you can guess that you are connected to that object that you are observing on the sun. It is a magnetic connectivity, so the other way to do connection is by magnetic fields. And Solar Orbiter has an instrument to measure the magnetic fields on the sun, again, the remote sensing part, but also the in situ part, a magnetometer that can tell us, well, our Parker spiral here looks like this, and this is what is predicted by phi. So through that, you can also make connectivity. There are two ways of doing connectivity, one through composition, one through magnetic fields. And then this is the main topic of Solar Orbiter, understanding this connectivity with the sun. I wanted to say that there is a big Spanish participation on Solar Orbiter, probably known to all of you. Two colleagues of mine, Professor Jose Carlos del Toro de Iniesta from Granada, is one of the principal investigators of SOFI, of the instrument that measures the magnetic fields. From the University of Alcalá de Henares, Javier Rodríguez Pacheco is the PI of the energetic particle detector. So this is the multi-messenger component. This is in situ, and this is remote sensing. So I think actually the Spanish solar community, solar and heliospheric community, is really well prepared to be able to participate into this multi-messenger era. This is the DKIS, this is Parker Solar Probe and the Solar Orbiter. Now I'm gonna go to just one science case that really demonstrates why it is important to have these combinations of measures, local measurements in situ with the sensors on Solar Orbiter and Parker Solar Probe, but also with the telescopes. The most important result that Parker Solar Probe has obtained is this, what is called switchbacks. The name in English is still being debated, but switchbacks is the one that is more commonly used now by the community. I'm proposing here a name in Spanish, which is latigazos, because I think it's like a latigazo on the magnetic field line. And here you have an impression of what we mean by these latigazos or the switchbacks. What occurs is that during the first encounter, already Parker, what we were expecting Parker to measure locally is the Parker's spiral, the spiral that I showed at the beginning of my talk. And it did measure the Parker's spiral. Here you have the magnetic fields locally measured by Parker. And this is the positive part of the Parker's spiral. Then it crosses the heliospheric current sheet, and that's the negative part of Parker's spiral. But it not only measured the Parker's spiral, it will also measure a lot of fluctuations, spikes on top of this Parker's spiral. This is not noise. Everything that you see here up and down and really high cadence, high frequencies, this is a magnetic fluctuation that even flips the polarity of the magnetic field lines. And that's why it has these switchbacks, right? So it's these S-shaped forms all over the place. and they are totally ubiquitous. Wherever Parker was flying, there were these switchbacks, and they were unexpected. They were seen before by other missions, but never with such a high density and such a high frequency of occurrence. So you get closer to the sun, you do see these switchbacks dominating the entire magnetic inner heliosphere. And of course, if you are bending the magnetic field lines, it's because there is a process that is dissipating energy, that is creating the energies, creating the bend to begin with. And if it dissipates energy, it can hit the corona. Hitting the corona, accelerating the solar wind is what we're trying to understand as the main component of the magnetic connectivity. And we think this is kind of the smoking gun of these processes that hit the corona and accelerate the solar wind, the switchbacks. We have just found them. I mean, it was reported less than 1 year ago, and the community is totally excited trying to understand what they can be. There are a number of theories for how the switchbacks can create, but all of them are trying to indicate that it's something that forms really deep into the sun, into the solar surface. And here you have one paper that was published less than a month ago about one of the theories. There are others, but I think this is the one that is now getting most of the attention of the community. So to produce these switchbacks, what has to occur is that this red line, the red line is an open field line that propagates into the heliosphere, encounters a loop that is closer to the sun. This is a closed field line. It interacts, it reconnects, and produces the S shape, and then the S shape moves away from the sun. We've detected this with Parker Solar Probe. That's one component of the multi-messenger. The other component now is go with the telescopes and really understand this process and understand how it all originates on the sun and what the position of energy occurs, how that can hit the solar corona and that can accelerate the solar wind. So that's what we will be trying to do with the telescopes on board Solar Orbiter and with Dickies. What we know now with existing telescopes is that the more resolution you have, the better sensitivity you have. This 10 to the 4 that I was talking about, these 0.1 arcseconds, you do see different polarities that you don't see with worse resolution. This is one satellite from NASA where you only see these black polarities here. If you go with better resolution, you will see these white polarities, and this is what you need to have for this interchain reconnection, for these different polarities that are interacting and reconnecting. So we need to do this with the telescopes on Dickies on the ground and with the telescopes on Solar Orbiter. Solar Orbiter is going to release the images tomorrow, I believe it is, the press release. And here you have Solar Orbiter observing the sun, and the ESA people already put here the switchbacks, as you can see. So they are very popular in our community, and we're all trying to understand the origins of these processes and phenomena. And you're really gonna need to have a multi-messenger approach to understand the physics. Measure them in situ, but really understand how it occurs on the sun. I think this is pretty much what I wanted to talk. This multi-messenger solar physics is explained in a white paper that we published, and it is online. It is on the archive, so I guess if you put my name, you'll find it relatively easily. And with this, that's everything I wanted to say, and I'm open to questions. Thanks. Muchas gracias.
Thanks a lot for this nice presentation. I think there are two questions. There is one from Benjamin Montesinos. Do you want Benjamin to do it yourself?
Okay, Valentín. Yeah, I wrote the question in the question and answer dialogue, but then I take the opportunity to thank you for the talk and for this, waking up. I see you're drinking
coffee, yes.
Triple coffee. No, I was, yeah, thanks for the talk. Now, I was asking just to do some futurology. With all this new instrumentation, probably you can read the question. You know that there are several problems in solar physics that are open already for decades. And I was asking you to pick one that you think that in the next 10 years, can we say that it is solved?
Yeah, as I was saying with these switchbacks that Parker has found, we really think is the smoking gun of the result of the processes that accelerate the solar wind and that are hitting the solar corona. You need to do energy, you need to do work to bend the magnetic field lines. And when you bend the magnetic field lines, there is a process like this interchain reconnection or whatever that could be, that is going to deposit some energy in the coronas. It's going to hit the solar corona and it's going to accelerate the solar wind. So we're really excited. I mean, this was not expected to find these switchbacks that often. So I think this is the one that we're really going to solve over the next 10 years or understand much better. Of course, we know it's not just one single process. It's going to occur in different conditions that we need to study with different positions of the solar orbiter and Parka solar program with the different orbital conditions of the Earth. It's going to be different whether you're observing a coronal hole, whether you're observing an active region, but we know that this is a process that really can trigger heating, can trigger acceleration of the solar wind. So we're really going to focus into understanding this, meaning we have measured them in situ. Now we need to see them with a telescope. We need to see them with remote sensing. And that's what we're going to be doing with mostly solar orbiter and Dickies. And the telescopes on the Canary Islands, they still can play a role there too, of course. Yeah.
Sure. Thanks.
Yeah. And thanks for the invitation. Thanks, everyone. I just read that there is a catastrophe in Tenerife, no light.
Yeah,
so.
there is a blackout. Yeah.
There is another question now from Jama Bestar.
Yep.
Please go ahead.
Okay. Hi, Valentín. Thanks for the talk. I would like to ask, because why an off-axis telescope is important to observe the corona?
Yeah, so I was really fast there. So the off-axis configuration is important because you don't have a spider and a secondary. In a regular telescope that is on axis, the first thing that the light from the astronomical object will hit is the spider and the secondary, on the back of the secondary, before hitting the primary. So that already generates a lot of stray light. And this stray light is a problem to see faint objects. So this off-axis configuration is interesting for us to see our faint object, which is the solar corona, but it's also interesting for doing exoplanets imaging to minimize the amount of stray light. So Dickies was designed from the beginning off-axis to really put this spider on the secondary off-axis so it minimizes the amount of stray light. You are hitting the primary mirror with pristine light from the sun that has hit nothing. And then your prime focus image is really, really sharp. And you can put there an occulter and produce like an artificial eclipse. So that's the combination. Of course, the Hawaii skies, which are really dust-free, help a lot in terms of our ability to observe the solar corona. So it's a combination of things, but being off-axis is really critical.
Okay, thank you.
Yeah. Thanks.
Bueno, muchas gracias a los tres, bueno, los cuatro ponentes de esta sesión de hoy.